Okay, so let me start with some just a small reminder from last time. We were talking about limits of stretch and anti-stretch lines, and I want to make a small, just a small remark, a small example. So we have a surface, say a surface with one cusp, hyperbolic surface, and then we take yes, okay, and let me take this example. I take an closed geodesic. I take say an ideal triangle, ideal triangulation where the leaves spiral along this closed geodesic. I mean, this leaf does not spiral, but these two leaves spiral along this closed geodesic. And then, so yeah, we saw that this is possible because when I cut along this closed geodesic, I get a pair of pants with one degenerate side, length 0, and then we saw that this is a union of two ideal triangles where the edges spiral along these leaves. Okay, so this is the picture. And then what we said is that the stretch line, the associated stretch line to this picture converged to the point on the Thurston boundary, which is this horocyclic foliation. This is my metric G. So I have this horocyclic foliation. Okay. This is what we said. We said something. We said something else. We said that we didn't say exactly, but I want to just to highlight this, the anti-stretch line, that is the stretch line traversed in the other direction, in the opposite direction. This converged to this curve, converged to the simple closed curve gamma. This is the simple closed curve gamma. This is proved in one of the papers. I gave you the reference, but the remark I want to say, you see, when we are doing this stretch, when we are doing this when we are stretching the transverse measure of this horocyclic foliation, of course this curve gamma here, so during the stretch, when the stretch goes to infinity, the length of gamma tends to infinity also. Right? You remember this because you see the transverse measure, the transverse measure of this horocyclic foliation when it goes to infinity, it means that the boundaries of these ideal triangles are stretched going to infinity, and then this curve, since they are spiraling along the length of this curve is going to infinity. Is this clear? So the only thing I want to mention is that you should not confuse the fact that even though the length of this curve is going to infinity, the hyperbolic structure is not converging to this curve as an element of the boundary of the Teichmüller space. It's on the contrary converging to this horocyclic foliation. The reason is that the horocyclic foliation, I mean, its transverse measure is going to infinity. You see, when a hyperbolic structure, and this is in the anti-stretch line direction. When I'm doing the anti-stretch line, the length of this curve is going to 0. Okay, and this is something I want you to. This is from Monday. The thing I want you to just to have an idea of this convergence is that it is when the length of gamma, when the length of gamma becomes very short, when the length of gamma becomes very short, it has a tube neighborhood which is very long, okay, and then well the length of the curves which intersect gamma, these are becoming longer and longer, okay, and so from the point of the on the point of the intersection number or whatever, this is the reason why I'm converging to this curve as an element of the boundary of Teichmüller space. Okay, this was just my small remark here to finish what we said last time. And now I want to talk about. I want to mention several other results after this one. You see, this is also related to my last week talk. So there are other cases. You see, there are other cases where I have a surface like this. Let's say like this with a geodesic lamination. Let's say with gamma. Now gamma is a measured geodesic lamination, which is not complete. Suppose gamma is not complete. That is the complement of gamma in the surface is not a collection of ideal triangles. It's something more complicated than ideal triangles. Then and assume that gamma is uniquely ergodic. That is, it carries only one transverse measure up to homotety. Now, uniquely ergodic. Uniquely ergodic. This means that uniquely ergodic. These are the foliations whose space of transverse measure consists of just one line. Assume that gamma is uniquely ergodic, and now complete gamma by adding by infinite curves, by infinite geodesic curves, which spiral around gamma. So if gamma is a simple closed curve, then we know what it means to spiral around gamma. If gamma is not a simple closed curve, if it's a general geodesic lamination, it's measured here, measured geodesic lamination. So the complementary components are not just triangles; they could be polygons. Like a spiral means that I'm just adding adding leaves which go here into the cusps. Okay. Then we have the same result. The anti-stretch line converge to the measured lamination. Now it's a measured lamination. Measured lamination gamma. If I don't have this hypothesis that gamma is uniquely ergodic, then I don't know. In fact, I don't know if somebody knows something about this. In fact, for me, it's unknown. I mean, there could be complicated behavior. This anti-stretch line probably will not have a simple, just a single limit.
And there we assume in the beginning that it is just one puncture, yes? This
was for my picture. No, I may have. It could be that I have no punctures also. It could be that I have no punctures also, and then I have these. And then I would have these. I would have these geodesics spiraling along one or several simple closed curves, and then I have this same conclusions. So there are results where this is. There are results like this one where the core geodesic lamination is a curve or a collection of curves. This is also fine, and there are results where it is uniquely ergodic. Note that when I complete this measured foliation gamma, like here or there, what I get is not a measured foliation. It is a geodesic. Lamination. It's a geodesic lamination, but it doesn't carry an invariant transverse measure. The invariant transverse measure, the fact that I said adding by infinite leaves which spiral along gamma, this is precisely because I don't want the resulting geodesic lamination to be a measured geodesic lamination. It has only one part which is a measured geodesic lamination, which is gamma. I don't want to add something which is measured, and this is why this is true. Okay, so now I finish with this, and now I want to talk about other stuff. I want to talk about some of the metric properties of the Thurston metric on Teichmüller space. This is the first thing. This is the first thing I want to talk about. I want to talk about 4 things today, so let's put them here. The second thing is the analog of Thurston's metric for surfaces with boundary. This is also something which I want to explain to you. The third thing is about the action of mapping of the mapping class group of the surface S, the action relative to this metric. I want to say something about the metric properties of this action. And then the fourth thing is the analog of Thurston's metric on Teichmüller space of the torus. And so this is for surfaces carrying the Teichmüller space of the torus is a Teichmüller space of the torus equipped with flat structures. This was also from Monday. I don't need this today. Okay, so what about the metric properties? You see, I want to explain just the results. I'm not going to give the proof. The proofs I will give you next time, proofs of part of these results, because otherwise it will. I will concentrate mainly on number 2 next time. But let me state all these results now. So you see, we have a metric space which is Teichmüller space equipped with a metric, and there are natural questions. For instance, is the metric complete? You see, we know. I mean, there are more classical metrics on Teichmüller space. One is the Teichmüller metric, which we know is complete. There is the Weil-Petersen metric. We had lectures on this at the seminar. The Weil-Petersen complete metric, we know it is not complete. So what about this metric here? Is this metric complete, or a related question, in fact, is are the closed balls compact for this metric? And this is the thing which I want to stress, in fact, which I want to point out, is that this is a non-symmetric metric. This is a non-symmetric metric, and the completeness and the fact whether the balls are compact or not. This is, I mean, you have to give them some meaning. It's not the usual meaning. It's not the usual meaning. And let me mention the name of Herbert Busemann. And this is in the, I think, starting from the 1950s to the 1990s. He always asks some questions about metric geometry. You know Busemann, yes? Yeah. This is the first American who got the Lobachevsky Prize, and he obtained it for his book, The Geometry of Geodesics, which is a marvelous book, in fact. So he dealt with non-symmetric metrics, and you see the problem with non-symmetric metrics like this Thurston metric. When you talk about these closed balls, there are two kinds of balls. In fact, you have the right closed balls and the left closed balls, and there are examples, and very interesting examples, of metrics where the right closed balls are compact, but not the left closed balls. And here in these examples, you see we have a very a very striking difference for this metric between geodesics when you go forward and geodesics when you go backwards. Sometimes the behavior is not the forward geodesics are not backward geodesics, and so on. And this is, I think, a very good setting, this Thurston metric, where somebody reading Boozman's work on non-symmetric metrics can find questions to ask and then try to answer in this setting of this geometric setting. You see, so Boozman wrote not only this book which I mentioned, but 3 or 4 books, in fact, on metric spaces, and in fact, a metric space, he added some axioms to the metric spaces, and I mean, essentially, he added the axiom that there exist geodesics between points. This is what he calls G spaces. G stands for geodesics. So he has his metric spaces have this additional property that there exist geodesics, and this is one example, you see, where we know that there exist geodesics between points. This is an asymmetric metric where we know that there exist geodesics between any 2 points by a result of Thurston, which I mentioned before. So so let me just note that in such a metric space you have, well, let's call it T. In fact, we were talking about Teichmüller space. Let's call it T, at a point G in T and R, a positive number. So this is, let's call it like this, B right, the right closed ball centered at G and of radius R. This is the set of metrics H, elements of Teichmüller space, such that the Thurston metric from G to H is equal to R, and the left, yes, yes, thank you very much, smaller or equal to R, and the left closed ball, this is the left closed ball, H, such that D of HG is smaller or equal to R. So, I mean, the results which I will state are easy to prove. They are not they are not difficult to prove, but still they need a proof. And they are the details of the proofs are contained in this paper. So this is a paper which I wrote with Guillaume Terret, and this appeared in 2007 in Math Proceedings of Cambridge Philosophical Society. The paper is called On the Topology Induced by Thurston Metric, and it contains these basic results on its topology, which are expectable results, but again they need a proof, and this paper is maybe, 20 pages long to prove them. So you see, it's easy to see that the topology, well, you have to define the topology induced by a non-symmetric metric first. You have to know how to define this topology, because when you have a metric, a genuine metric on some set, then you take the closed balls, or if you want to deal with open balls, you take the open balls, and you know that you show, in fact, that the collection of these open balls give you sub-basis for some topology, and this is the topology. Okay. Here, if you take the right balls and you try to do things, you'll not be able to prove that they give you a topology. You have to. I mean, there are some complications, and so you cannot just reason with these balls or take. The thing that Busemann says is that while in fact for non-symmetric spaces, the topology is the one induced by the symmetrization. So by the symmetrization, ds of xy equals d of xy plus d of yx. So this is now a symmetric metric, and then you just consider the topology induced by this metric, and it's easy. In fact, it's easy to show that in this sense, the topology induced by the Thurston metric is the usual topology. The usual topology on Teichmüller space, the topology induced by the Fenchel-Nielsen coordinates, or the topology induced by quasi-conformal mappings or anything. The problem with this stretch, with this best Lipschitz, the Lipschitz mappings, unlike quasi-conformal mappings, I mean the best Lipschitz mappings, the inverse is not, the inverse of a best Lipschitz mapping is not usually it's almost always not a best Lipschitz mapping and so on. So you have to, the metric is non-symmetric. But anyway, so this is the topology. This is the top. It's easy to see that the topology here is the same as the one of the induced by the Teichmüller metric or the Fenchel-Nielsen coordinates. But the question is about the completeness. So here are the results which I want to state. So I will be a little bit redundant because some results are used to prove the other results, but I will state them so that they are clear. Okay. So the first result is that, okay, let Gn be a sequence in Teichmüller space which converge to infinity. This means that it is outside the compact set K, and here I have to put for any compact set K, it is outside the compact set K.
Compact, you mean
yes.
with respect to this symmetrized metric to the usual? Or to
yes. Yes, I said it's the usual metric, so the fact that it's compact or not, no, it only depends on the topology. You're right, depend to any one of these metrics outside the compact set for n large enough. Well, this is equivalent to either for any h in Teichmüller space, the Thurston distance from h to Gn goes to infinity, and then the second thing is that for any h in Teichmüller space, distance from G to H, Gn to H goes to infinity. If you think a little bit about how this metric is defined, using Lipschitz maps and then using the lengths of simple closed curves and so on, this I mean, this statement is this equivalence between these three things is not trivial. You have to prove it. Okay. Yes.
Examples that something goes and the other one does not. What way it goes?
Yeah, I have to give you. I have to define. Yeah, metric. Example of metric spaces.
Yes. Examples of this Gn. Is there an example?
No, this Gn there are no examples because this statement is true in Teichmüller space. If I want to give you an example where this is not correct, then I have to take another metric space and not this one.
No, I mean, so you say, apparently these two claims are not equivalent.
In this, I have three claims. Yes, I have three claims. The three of them are equivalent.
Well,
The theorem. Yeah, maybe I said this is a definition. You see. That Gn converts to infinity,
yes,
okay? And I'm saying that this is equivalent to this claim and also to this claim. So I have three claims which are three properties which are equivalent. And if you want me to give, yes. So there are examples of metric spaces where with non-symmetric metrics where this is not equivalent to this and this is not equivalent to this. Yeah. Okay. And the second theorem, which let's keep this. The second result now about this metric is. Is that the two kinds of balls, the left and the right closed balls, are all compact. And you have examples of metric spaces where this is not true. So one example is this. This Funk metric, which I talked about one day. So you have a point here. You have a point here, x, and a point y here. And the distance from x to y is this Euclidean distance to the boundary divided by this Euclidean distance to the boundary. So this is an example of a space where I think the right closed balls are compact and the left closed balls are not compact. Okay, so the third result is about the completeness. Let's put it here. You see, as I said, the Teichmüller space carries this Teichmüller metric, which we know is complete. It carries this metric, which this metric also will be complete. It carries the Weil-Petersen metric, which is not complete. This one is complete, and then you have to. There's in fact, as I told you, it is Busemann who introduced all these notions for non-symmetric metrics. So he introduces the notion of completeness, and to introduce his notion of completeness for non-symmetric metrics, he puts as an axiom. He has Otherwise, things are very complicated. I mean, you don't get interesting notions. So this is for spaces, for metric spaces, that satisfy this kind of property. But you see, for converging to zero instead of to infinity, and let me tell you how. So the three properties are equivalent. The three following properties are equivalent. The first one is for every h and for every gn in Teichmüller space, for every point h and for every sequence gn, while d symmetrized of gn and h goes to 0. This is the usual notion of convergence for the symmetrized metric. The second thing is for every h and for every gn. No, sorry. Here I don't have symmetrized. Okay, this is the metric. D h of gn goes to 0. So this is the convergence to the right. This is convergence to the left. I could have kept the first one, but I prefer to put it like this. For every h and for every gn, this is the symmetrized, and this does not. For the symmetrized, the order does not count. So this is the third theorem is that the third result is that this is true. This is true for Thurston's metric. This is true for Thurston's metric, and then you can use the usual notion of completeness, where and this usual notion of completeness saying that well, when you have a Cauchy sequence, then for any Cauchy sequence it has a limit. Any Cauchy sequence has a limit in the space, and then the convergence is for anyone. You can use either the left or the right or the symmetrized. So this is the right notion of completeness, I think. And the
Cauchy sequence will be just Cauchy sequence and symmetrized metric.
Yes, right, exact. You can use a symmetrized metric. Yes, right.
So this is just completeness of symmetrized metric.
It is completeness of symmetrized metric, but instead of completeness of symmetrized metric, you can use either one instead of the symmetrized metric. This is the point. You can use either one, and so this is the point. So this is. I mean, these are the few metrical, topological. I mean, when you talk about compactness and so on, this is topological. Then metrical and topological questions, which I know how to answer concerning this Thurston metric. And now I want to. In fact, okay, this is correct. I want to go to number 2 now. It's number 2. It's number 2 which I want to expand more because there are a lot of interesting properties for number 2 which are still not proved. I mean, I don't know the answer for them. There are a few papers, maybe 5 or 6 papers on this number 2 here, analog of Thurston's metric for surface with boundary. But I think there's a lot of work to do still a lot of work to do. Let me tell you what is. So this I will explain. I will expand this next time, because now I want to go into these 4 things. But let me tell you what is the main problem with surfaces with boundary. So let's take a simple surface with boundary, and this is a pair of pants. So I'm taking hyperbolic structures with geodesic boundary on this this topological pair of pants, and think about. So you remember we had this 2 versions of Thurston's metric. We have L with the Lipschitz constant, with the best Lipschitz constant, and we had K with the this was this logarithm of the so let's put it K of GH to be more precise. K of GH, the logarithm of the supremum over gamma of H of gamma, G of gamma. So this is gamma, well, simple closed curve. I'm taking this supremum. Remember this. Now we know. Okay, so that's a question of taking or not in gamma simple closed curve, including or not including the boundary curves. If I don't include the boundary curves, then there's no simple closed curve here on the no simple closed geodesic on this pair of pants. So the theory does not give me anything. So I better include the lengths of the boundary curves here. And you remember we said that. Did I use L? I did not. So this is L1, L2, L3. We said that L1, L2, L3 parameterize the geometry of this pair of pants, right? When I give you L1, L2, and 3, then I have a unique pair of pants up to isometry. Well, it's easy to see that in this case, there are G and H such that this distance is negative. Okay? Right? This supremum can be less than 1. And then the logarithm is negative. And I don't want to deal with this. In fact, I want to have a metric on this. I want to have a metric on my space of pair of pants, but this is not the right one. When you find something, when you define a natural metric like this one, and you notice, well, for some pairs of points, the metric is negative. One possible way in which you can go is to say, okay, so I have some more structure on this Teichmüller space. You see, I have the notion of points whose distance is positive, and these are the good pairs of points. Remember that K of GH depends on the order of G and H. So when this distance is positive, for this formula here, it means that H is a point which I can attain by a geodesic from G. So I have a notion of, notion of future H is in the future of G. I have a new structure. For each point G, I have points points H in its future, points where the distance is positive. I can go like in general relativity, you know. And then I consider only these for my metric. I forget about the distances, negative distances. I forget about the points where I don't want to go there because the distance is I cannot go in the future the distance. So I could work with this, you know, and I don't know how to. I mean, I never experimented this. I never pursued this further. But I think that there is something here which you can do. And for surfaces which are more complicated than pair of pants, because of this, this result here, this is, let's call it a theorem. And this is a theorem. This is a theorem which is again with I proved with Terre, and this is in 2010. I don't remember whether it's before or anyway. So this is proceeding of AMS, and in this theorem is called shortening all the simple closed curves in a hyperbolic surface. In fact, it's not only about simple closed geodesics. I think it's not only about simple closed geodesics, it's shortening all the geodesic, I think, but I have to think about it. But in this paper, it's only about the simple. So the result here says that not only the pair of pants, but for any surface with boundary, for an arbitrary surface with boundary G, hyperbolic surface, of course, with geodesic boundary, there exists a hyperbolic surface H such that this distance k of Gx is negative. So this phenomenon is it holds for any compact hyperbolic surface with boundary. And the same discussion which I said here, it works. A good question is you have a surface with boundary, and you want to define the notion of a future, and you want to study you want to study the geometry of this metric defined only on pairs of points G and H, such that k of G of H is positive or zero anyway. So, but this is not what we do in the first paper. I don't know if I gave you the reference for them anyway. So this is the analog of Thurston's metric for surfaces with boundary. We change the metric. And we define a new metric, which I want to tell you. And this is also a general way of thinking, a general method, you know. So this I don't need. This I need. So for surfaces with boundary, so instead of simple closed curves, simple closed geodesics, we deal with arcs. So instead of considering the simple closed geodesic in this surface, we deal with with arcs like this one, or this one here, or this one here. I drew them in this special case, but here I have all these arcs like this, and another arc here. Okay, so what are these arcs? These arcs are arcs, geodesic arcs joining boundary components and minimizing distance minimizing between them, distance minimizing between the boundary components.
So you don't take long geodesic, which binds several times?
No, these are compact arcs, yeah, compact arcs. Mm-hmm. Compact arcs, when I say arc, it's not.
Yes, right.
Yes, I don't take this. So.
No, the other homotopy type connecting two boundary components.
There are no others. It's only, you see, here in this pair of pants, you don't have any others.
The pants, yes, but in the
there.
pants,
Well, yeah, here you take them all.
everything.
Here you take everything. Here you take everything. And now there are some basic geometric results which you need. For instance, if you believe the fact that in any homotopy class of simple closed curve in the surface there is a unique geodesic. This is a theorem of Hadamard of 1916. This is a basic theorem in surface of negative curvature. Then you believe also the same proof applies. You see, Hadamard, I think he uses proof by calculus of variation just to find a minimum for this length function. The same thing here. Or if you want to use this result for existence and uniqueness of simple closed curves, to prove existence of and uniqueness of simple closed arcs, minimizing arcs, you just take the double of the surface and you reason with the double of the surface, and then because of the symmetry, this arc is always perpendicular to the boundary. You don't need the symmetry to show that this is perpendicular to the boundary. I mean, if it were not perpendicular to the boundary, then you can take a shorter arc. This is also a fact of a small fact of hyperbolic geometry. You see, you have a geodesic here, segment, and here a point. The shortest arc is perpendicular. It's like in Euclidean geometry. It's not true in any geometry, you see, but this is special to these geometries. Okay. This is so now when I have these geodesic arcs joining boundary components here in gamma, I can use the same formula now. I can try to use the same formula, and here gamma is, well, this is the set, the homotopy class of arcs. Or if I don't want to say homotopy class, then I say geodesic arcs joining boundary components. Arcs joining boundary components. So there are several versions here. But it turns out that all of them, they give you the same thing. You could add to these arcs, union the the union the boundary curves. So you allow gamma to be either a geodesic arc joining two boundary curves or a boundary curve itself. You could also allow, while the closed simple closed curve in the surface, and it turns out they give the same thing. Anyway, you get a metric here. You get a new metric, and this new metric does not have this funny property. The new metric, for this new metric, everything is positive. The distances are all positive, and this new metric we called it the arc metric. The arc metric for surfaces with boundary, and you want, of course, when you have such a metric, you want to see whether all the properties of Thurston's metric hold for this arc metric. It turns out that some of them hold. For others, I don't know. There are still open questions for this arc metric. For instance, something I don't think I will have time to talk about this here. Something again related to Boseman work, and the philosophy of Boseman is always to look for metrics which are Finsler metrics. That is, the main question. When you have a metric space, satisfying the additional Boseman axiom on existence of geodesics between points, and something about you want to know whether the extension of this geodesic or not. This is a little bit more technical, but the important thing is the existence. So you want to know whether this metric is a Finsler metric or not. That is, whether this metric is sorry, there are more fundamental problems, but let's say, okay, so one of the fundamental questions in Boseman's work with this, when you have a metric space with these additional axioms, a small list of additional axioms, maybe 2 or 3, about existence of geodesics and the extension of geodesics. The main question, I think, which is still unsolved in the general case, this is whether your metric space is a manifold or not. Okay, and there have been some progress on this problem very recently by two people I know very well. In fact, one is in Novosibirsk. This is Berestovsky. Do you know him? Berestovsky? Yeah. Okay. So he has a result in this direction on this Boseman problem, and the other one is also Russian, and his name is Andreev. Pavel Andreev, do you know him?
Pavel Andreev? No.
Yeah, so he worked in the University of Arctic. Is there a University of the Arctic here in Russia? Very north. A small university. It's called his address is University of the Arctic and so on. In fact, I know him, and unfortunately, I received very recently an email from Berestovsky telling me that Andreev passed away after a surgery. It was a very, very simple surgery, but I don't know what happened. And he was very young. I think he was around 45, something like that. So, okay. So there have been progress on this. The other. So after after this problem, whether these metric spaces are manifolds or not, there is. Let me mention also that Berestovsky and Andreev, they proved that this conjecture, or that this metric space with the Boseman axioms is a manifold under additional conditions. The one additional condition is non-positive curvature in the sense of Boseman. And the other additional condition is, which is different condition, non-positive curvature in the sense of Alexandrov. So under these two additional conditions and two separate works, this metric space is a manifold. So the other thing is that suppose you have a metric space which is a manifold and which satisfies.
I did not understand. So we look at the space of all hyperbolic structures on a given surface with a boundary.
Yeah.
It is unique. How can you put additional conditions?
No, I'm talking now about this general properties of metric spaces in the sense of Boseman. And
so their work was about just.
This Boseman question, it was a digression.
And this additional condition, do they hold for our space?
This is a very good question. I mean, they prove that under this additional condition, the space is a manifold. But we know that our space is a manifold. So this additional condition will not help us in this. But the question you raise is very interesting because they work in the setting of symmetric metrics.
How do we know that our space is a manifold if we look at it not from the viewpoint from Frenkel-Nielsen?
Yes, because as I said, this topology induced. Topology is the same. Topology is the same.
Then we know.
Yes. So we know. Yeah.
Then why we care about Berezovsky and Andreev's result?
Because Berezovsky and because I was talking about this fundamental problem of Boseman on Boseman spaces, I want to talk about one fundamental property which we care about, and I said this is a fundamental property. But then I said that in fact, there's a more fundamental property about Boseman spaces it's whether they are a manifold or not. Okay, and then I mentioned Berezovsky and Andreev and so on, and now I come to the other fundamental property which. When we know that they are manifold, whether this metric comes from a Finsler structure, that is, whether it comes from an infinitesimal norm on tangent spaces, and whether the length of a path, the length of an arc, you can measure it, the length of C1 or piecewise C1 arc, you can measure it by integrating these norms. Okay? If this is true, then your manifold is a Finsler manifold. And one of the results of Thurston for his metric is that the Thurston metric is a Finsler manifold. But I don't know whether the result is true for the arc metric. This is an unknown. This is an unknown question for the arc metric. This is an unknown question for the arc metric, and I wanted to say something more. So, in fact, you see the main technique which people use to show that some metric is Finsler or not is a theorem called the Boseman-Meyer theorem. Boseman-Meyer theorem. Which could be used, in fact, but to use this theorem, you have first to answer a preliminary question whether for this arc metric any 2 points can be joined by a geodesic. And this is an easier question. This is prerequisite, of course, because for a Finsler metric, any 2 points by definition are joined by a geodesic. But this question of the existence of geodesics joining two arbitrary points for the arc metric is unknown. I don't know the answer. So for number 3 and 4, maybe we do them after the break. Now we are I want to talk about number 3. And this is the action of mapping class group relative to this metric. So I want to tell you what are the things we can say about this. So this is these results are in a paper, in fact, with. I want to mention my co-authors. In fact, this is Liu and Su. These are my Chinese co-authors, and again Tere. And so we have this in Math Proceeding of Cambridge, and this is 2013. So we are getting closer and closer to today. And maybe I want to say also that the action, the analog of Thurston's metric for surface with boundary, that is the arc metric. The arc metric. I have also collaborators for this. So this is, I have Liu, I have Su, I have Tere, some papers with him, and then Alessandrini. So not all of them in the same paper, but a mixture of these people. Okay, so now that I have mentioned what the people I have to mention, let us do the mathematics. So let me tell you what. So there's this action of gamma. Let's call gamma the mapping class group of S. Okay, so what about this action? What can we say about this action? Let me just remind you of something we already talked about, that we have Teichmüller space, and we have Thurston's boundary, a sphere. This is a ball, this is a sphere, and the union is a closed ball. This is a theorem. It's not always true that if you glue a sphere on a ball you get a closed ball, but this is part of Thurston's theory. This is projective measured foliation space. And then let me remind you that there is this Thurston's classification. Thurston's classification of elements of gamma. So again, I don't care today about whether the elements of gamma are orientation preserving or not. This is, I mean, we have to deal with this if we talk seriously about this. If we are writing a paper, we have to. But let's not deal with this. So Thurston's classification of the elements of gamma is obtained. I mean, Thurston obtained it by analyzing the action of a mapping class that is an element of gamma on this we call T bar. Okay, so what is this? What does this tell us? In fact, this is purely topological. There is no metric at all. And then later, I mean, in this number 3, I will talk about an action of the mapping class group of the surface, but something that uses the Thurston metric. But now let me recall this classification, which does not use any metric. So, okay, so I have a homeomorphism. So gamma. So let's say an element of gamma. And I don't want to call it small gamma because we already used small. Well, yeah. Okay, let's call it small gamma. Anyway, yeah, small gamma acts on on T bar as a homeomorphism, and it has a fixed point. Again, this has nothing to do with Thurston metric. I'm recalling Thurston's compactification and the action of gamma. So I know that when I have a homeomorphism of a closed ball, I have a fixed point. So there are two cases. Either the fixed point is in Teichmüller space, in the open ball, or in the boundary.
Well, it can be that it is inside the Teichmüller space.
It can be.
Can be.
Yes, it can be. It can be. This is you see when you have a suppose you have a Riemann surface or a hyperbolic surface which has some symmetry. Okay.
Yes. Yes,
Okay. Then okay. And this is the only case, in fact.
Yes.
Okay.
Well, that's good because that's my goodness, I have no intuition.
Okay. So so if the point is in T, then in fact we get a Riemann surface, either a hyperbolic surface. When I say a Riemann surface, means that I forget the hyperbolic structure. I'm talking only about the complex structure. But the two, I mean, the two are equivalent, but it's better. The best thing is to pass from one to another in each sentence. I mean, every time you have to pass one to the other, because things become easier when you think about a complex structure, and other things become easier when you think about hyperbolic structures. You have to be skillful in the two things. So we get a Riemann surface, and this is we get a Riemann surface fixed by let me write it like this: homeomorphism of the surface. So in fact, you don't get immediately this because everything is up to homotopy, right? You get a homotopy class of a homeomorphism which is fixing some Riemann structure, but then by some theorems in Riemann surface theory, suppose we have a closed Riemann surface, if a Riemann surface, so a surface equipped with a complex structure is, you see, if let's put it like this: if I have a homeomorphism homotopic to the identity which sends a complex structure to itself, then this homeomorphism is the identity. And more generally, if you have a mapping class, an element of the mapping class group that is a homeomorphism up to homotopy, which fixes a Riemann surface structure up to homotopy, then in fact your mapping class has a representative which is which fixes this Riemann surface structure and which is periodic. So let me put it like this. An automorphism, or the automorphism. This is a statement. The automorphism group of a Riemann surface is always a finite group. This is stronger than what I said, and this implies that if gamma has a fixed point in Teichmüller space, then gamma as a mapping class is periodic. Okay, so this is of course the 2 points, the two things are not disjoint. It can have a point in the interior, and also it can have a point, a fixed point on the boundary. The next thing, so let's say now if gamma has a fixed point in PMF,
then there are closed leaves.
No, not necessarily. And here there are two cases. You are right. There could be closed leaves.
Oh, it's not feeding, not association.
Yes, right, exact. So there are two cases. Either a fixed point f, let's say a measured foliation f in PMF. So either f has closed leaves, as you said, then gamma, well, it fixes a collection of simple closed curves which correspond to these closed leaves, a collection of disjoint simple closed curves. So here I have to be careful, because the closed leaves could also be closed leaves joining singular points, closed leaves made of arc joining singular points. I don't want to enter into this because this is not my topic anyway.
And
so
this is bad.
No, this is good also. It can have, yeah, it's also good. Yes. The other thing is that,
by fixed collection, you mean as a set, so it can permute it.
Yeah, it can permute. So on the surface.
Here there is also a symmetry case for measured foliation can also be symmetry.
Yes. If it has a symmetry, it could have a symmetry, but without closed leaves or with closed leaves, it could. Yeah, right. Yeah, so you are right. I can talk about instead of I talked before about the symmetry of a hyperbolic metric or of a Riemann surface of a complex structure, but we can talk also about the symmetry of measured foliation. You are right. This is important. It will not appear here, but it's an important issue. So anyway, let me try to finish this statement without making a mistake. Then gamma fix a collection of simple closed curves. So on my surface, I will have some set of simple closed curves which could be permuted. In my example, these cannot be permuted because one is non-homologous, the other one is not. So these could be permuted. And then F is called reducible. You see, F is called reducible. In the case F is periodic, First case. In this case, if there is a fixed closed leaves which are fixed, permuted, then f is called. It's not f which is called reducible. It is gamma which is called reducible. The reason for this word reducible is important, in fact, because when it fixes these homotopy classes of curves, then you can cut your surface along these curves and consider the action on the resulting surface, the action on the surface with boundary, which is less complicated than the initial surface. So you have reduced your complication. So you have now you analyze the same action. Well, you analyze the action of gamma on the Teichmüller space of the reduced surface, and you continue. So it could be so this reduced surface obtained by cutting along these curves has its Teichmüller space. You have a mapping class acting on this surface. You consider the mapping class group of this surface. You have reduced the genus or whatever. You have reduced the Euler characteristic of the surface and so on, and you continue your analysis. Either or f has no closed leaves. No closed leaves. And this implies that every leaf of f is dense. Every leaf of f is dense. We already talked about this at some point. I told you that there's a decomposition of measured foliation, and you decompose them by cutting along the leaves, joining singular points, and so on. So we know that every is dense. And here there are also two cases, in fact. Let me just recall that this is an action. We are considering an action on PMF, the projective measured foliations, not the measured foliations, PMF. Okay? And here also this action on PMF. So in fact, action on PMF, it means that I have a measured foliation. When I said that I have a fixed point on the boundary, it means a measured foliation, but which is preserved up to a multiple, up to a constant multiple, right? And this constant multiple here, it's either equal to 1 or different from 1. If it's equal to 1, it means that I just have a symmetry of some measured foliation which has no closed leaves. Okay? And this implies that my map is finite order, like in the case of Riemann surfaces. So what you said is used here. The other case is that this factor, we said that this measured foliation is preserved up to a factor. This factor is different from 1, and this is the case which Thurston called pseudo-Athanase, which generalizes the Athanase homeomorphisms of the torus. Athanase was not in St. Petersburg, right? He was in Moscow. Anyway, so this is Thurston's classification. So everything is. I mean, this is a classical stuff. Everything is topological. You don't use any metric. And now I want to use the metric. In fact, I want to use the metric, and I must say right from the beginning that we were not the first to use the metric structure of Teichmüller space in order to study the action of the mapping class group, because there was also so the use of the, let me put it here, the use of the metric structure, of Teichmüller space to study the action of mapping class group. So what metric structure? This is for the Teichmüller metric, the use, so after Thurston proved his theorem on the classification, this was done by Beers. He classified again the element. He made this classification of the action using the Teichmüller metric and the action of the Teichmüller metric. And then for the Weil-Petersen metric, this was done later. This is I think in the 1980s. This is by Daskalopoulos and Wentworth. This is 2000 something, maybe 2008 or maybe, I don't know. And then for the Thurston metric, use the Thurston metric, and this was done by me together with the three people I told you. You, Sue, and me, and Tere. And this is 2013. Anyway, so let me tell you how it works. So we come back again to ideas which I read in Guzman. He always has very, very good and very simple ideas. So you have where is the chalk? You have a metric space. You have a metric space, say X, and then you have F, a homeomorphism of the metric space, and then you define something which is tau of F, called the translation distance of F. So when you have such a situation, you see you're thinking about a very simple example, say of hyperbolic space and an isometry. So this is an isometry, right? Otherwise, you don't get anything interesting, I think. I mean, yeah, you could get something interesting. You could classify things general than isometries, maybe projective maps if you have projective structure, or homotheties or things like that. But let's stick to the isometry, like isometry space, like isometry of hyperbolic space. So so you define the translation distance here as the infimum of the distance between x and f of x, and you take the infimum over all x in your space X. And you see what you get. If you get something, if you can say something interesting about this. And in general, so the first trivial, so the first thing you notice, the first thing you want to notice is that, well, either tau of f is 0 or tau of f is strictly positive. Okay? And then in each case you have either is 0 or attained by some x in x, or not attained, or here too, if it's strictly positive, either attained or not attained. This is something you know in Lie groups, right? You're a specialist of Lie groups. You have this kind of thing.
I'm not a specialist.
What you told me.
Attained what?
Okay, so attained by some. So this is an infimum. This is an infimum. Yeah, attained by some x or not attained, and then there's some classical terminology. I thought it comes from Lie groups, but you're saying that doesn't come from Lie groups. This is called.
I see that I don't know Lie groups.
I don't know. You told me once that you are a specialist of Lie groups.
No,
this is
no, that's not true.
okay. The first day I met you told me this.
Well, I
Okay.
hope
Yeah,
I didn't
okay.
tell you.
Yeah. Okay. Yeah. I thought this. Something. I thought, it was the first day I was here, and everything was new for me. And maybe I mixed you with somebody else, and somebody told me that he works on Lie groups. Anyway, this is attained by some x. So this is called. So what is this? Okay, I better not. So this case is usually called. Okay, yeah, this is elliptic. In this case, we say that f is an elliptic isometry. In this case, the usual terminology is that it is parabolic. You see, it's like in isometries of hyperbolic space. This is called hyperbolic. So these are the three cases in the hyperbolic isometries of hyperbolic plane. But here we have an additional one. This is called pseudo hyperbolic. And then we analyze. We take this definition. We take this definition here, and we see what we get for the Thurston metric, and we try to compare to the Thurston classification of mapping class groups. This is the thing. So this is what was done by Beers for the Teichmüller metric, and then Lascalopoulos Wentworth for the Peterson metric. So let me explain this. I will state the results, and then you will understand. In fact, number 4, I will do it next time, because it's time for lunch, and especially it's time for my nap. So let me give you these statements here. In fact, I have 5 statements. Okay, some of the statements involve the Thurston classification and the action of the mapping class on the Thurston metric without, only with reference to Thurston classification. So the first result is that if I called it gamma. Okay, the mapping class is called gamma. If gamma is pseudo-Anosov in the classification of Thurston, then it leaves invariant it leaves invariant a geodesic for Thurston's metric. This is one result. This is one result which makes it so it is at I didn't say yet that it acts as a translation on the geodesic. I didn't say yet that for every point on that geodesic, like in hyperbolic space, you see if you yes.
Definition X is a hyperbolic surface, right?
Okay. No, this was a space. This was any metric space. Any metric space, and now I'm specializing to X. X is Teichmüller space. And F is a mapping class, is an action of an element of the mapping class group.
Okay.
And in fact, it leaves invariant a geodesic, and so we talked about stretched lines. I told you that these are examples of geodesic, but I told you that there are other geodesics. I will say later, not today, but later, how you can find other geodesics. But this geodesic here is not necessarily a straight line, but the statement is that there exists an n, there exists an integer n, greater than 0.
The
yes.
classification doesn't depend if we swap x and f at x, because mathematics is not non-symmetric. So
you are right. You are right. It depends. It depends. It depends. It depends. Let me mention that there is another metric on Teichmüller space where you switch the two. And this metric, I don't know anything interesting about that metric. It's completely different metric. About its geodesics, about its, there are things, whether it is, there are many things which I don't know about about its isometries, for instance. I don't know. Yeah. This is something which if somebody is interested, he can investigate this. So there exists an n such that gamma to the n leaves invariant a stretched line. You see, stretched lines are examples of geodesic, and here I come back to Busemann because he he introduced terminology. In fact, he introduced this notion of spaces with distinguished geodesics. You don't need to read what he said, but the idea that you have some metric space and you have a notion of geodesics which are easier to deal with than others, the distinguished geodesics, you see. And this is, I think, very interesting and could be applied here. These distinguished geodesics in this setting are the stretched lines, either the stretched lines or concatenations of stretched lines. I don't know what is best to develop such a theory. You see, Busemann was interested in this Hilbert problem number 4. Hilbert problem number 4, which asks to characterize the metrics on subsets of Euclidean space where the Euclidean lines are geodesics. But you can have other geodesics, but these are distinguished geodesics. You see? And he worked on this problem. And then he modified it a little bit because the metrics may be symmetric or non-symmetric. The symmetric case, in fact, under differentiability conditions, And for symmetric metrics, the symmetric metric case was solved by Pogorelov. You know Pogorelov, right? And he used ideas of Boseman. In fact, he says in what he wrote about this. In fact, the story is that Boseman came to Moscow. I don't know, in the 1960s. This was the first time he came to Russia, and he explained a method of constructing such metrics that satisfy Hilbert number 4. A method of constructing such metrics that is metrics on Euclidean, say Euclidean convex sets. In fact, it's sufficient to consider convex set where the geodesics include the set of geodesics include the set of real lines. And then he explained a method using how do you call this geometry? Integral geometry, where you see where so anyway, I don't want to say a lot about this. And Pogorelov, after he heard this lecture, he showed that in fact all of them all of these metrics are obtained using Boseman's construction. In fact, all of these metrics that satisfy Hilbert problem number 4 are obtained using Boseman. So anyway, the thing I'm saying is that there is a notion of space of distinguished geodesics, and this Teichmüller space equipped with the Thurston metric is such a space, and this is different from the Teichmüller metric, and different from the Weil-Petersen metric, because in these two metrics, 2 points are joined by a unique geodesic, whereas in this space there are many, in fact. And one good question is to describe them all, but I'm not going to talk about this here, and I don't know the answer to how to do it properly. So, but anyway, there are these stretch lines which we talked about, and a pseudo-Anosov mapping class lives invariant at geodesic, and up to taking a power, this geodesic is one of our distinguished geodesic. Okay, the second statement is again, if gamma is pseudo-Anosov, then this translation distance of gamma is equal to the translation distance of gamma inverse, which is related to the question you said there. So there is something positive for pseudo-Anosov, not in general, and in fact something which is unexpected, very interesting, I think, and it's also equal to the tau of gamma translation distance, but the translation distance for the Teichmüller metric. And this is kind of surprising because the metrics are very different. This metric uses quasi-conformal mappings and things like that, quasi-conformal theory analysis. This metric is purely geometric. It uses elementary hyperbolic geometry, ideal triangles, and geometry of ideal triangles and things like that. I have several other things to tell you here on this metric, but maybe we stop right because now it's time, and then I will continue next time.
So this is the end of this theorem. So
this is the end of this theorem, but there are several others. There are several others. If I do them, I will do them. I will do them very quickly, and so this is Mm-hmm. Yeah, I would need maybe 20 minutes for this to finish this, and then I have number 4, the Teichmüller space of the torus, which is also related to this. In fact, I prefer to do this next time. Mm-hmm. So next time will be in 2 weeks, and I will give. We said that I will give 2 lectures, right?
That is the best.
Yeah. Okay.